He's an industrial PhD student at KTH in Stockholm, working at RISE in SICS. His main research interests include computer networks, surprisingly, NFV and SDN, with a focus on high-performance packet processing. And today, Georgios is going to present Metron, which is an NFV service chain of the true speed of the underlying hardware. Georgios, the floor is yours.
Thank you very much for the introduction. Hello, everybody. My name is Georgios, and I'm going to present you Metron, an NFV service chaining platform that operates at the true speed of the underlying hardware. This is a joint work with Barbette, Dejan, Kostic, Steinert, and Gerald Maguire. Internet services have become an inextricable part of our lives, as billions of users from all over the world are vigorously accessing internet content on a daily basis. This puts a lot of pressure on network operators as they need to satisfy key user requirements, such as high throughput and low predictable latency. This is not very easy to achieve though, as in reality, internet traffic goes through several processing functions on its way to the content and back. These functions, also known as network functions, can be routers, firewalls, load balancers, etc. In an attempt to provide very exciting new services for the users, network operators typically chain network functions together, composing different service chains for different types of applications, usually each serving different amounts of load. This further increases the processing demands in the network. Therefore, it is imperative for network operators to minimize the performance impact of service chains. Recent studies have shown that link speeds in data centers, such as Microsoft, have exhibited a 50-fold increase between 2009 and 2017. This will soon become a 100-fold increase with the introduction of 100 gigabit network interface cards in these data centers. During the same period, transistor counts have not exhibited the same rapid increase. Specifically, transistor counts have are doubling their counts every usually two years, while, as we have seen from this graph, link speeds do so much more frequently. The problem here is that service chains today, as per the NFV or Network Functions Virtualization concept, greatly rely on CPU performance. And this is because an NFV service chain is usually deployed on general purpose processors on commodity hardware. Therefore, in this work, we would like to answer the fundamental question whether existing NFV systems can operate at these emerging link speeds at 100 gigabits per second or beyond. To answer this question, we have deployed a 100 gigabit testbed that consists of two commodity servers. One server is used as a traffic generator and receiver, while the other server is used to deploy a stateful service chain of a router, followed by a network address and port translator and a load balancer. First, we would like to measure what is the maximum attainable throughput of this testbed. And to do so, we deployed a simple forwarding function on the processing machine. This function reads packets from the network interface card and immediately bounces these packets back to the origin without performing any processing. This results in 76 gigabits of total throughput in this testbed. And the reason we cannot achieve line rate throughput is because we injected a real trace that consists of a large fraction of small frames. And this Mellanox card used by the testbed is not able to process such small frames at the line rate. Next, we deploy the example service chain using an emulated version of the E2 NFV framework presented in SOSP 2015. To emulate E2, we use Core 1 as a dedicated software dispatcher that interacts with the network card and passes input packets to the overlay functions running on the remaining CPU cores of the system. This is because the graph with the yellow triangles starts from Core 2. As we can see, the throughput of E2 linearly scales with increasing number of CPU cores, but up to a certain point. After using more than 12 CPU cores, this system is not able to operate in a linear fashion, and there is a performance degradation in throughput at around 12 gigabits per second. Next, we deploy another state-of-the-art system called OpenBox for the same service chain. From the green circles in this graph, we observe that OpenBox clearly outperforms E2, but it is still unable to obtain or achieve the maximum attainable throughput of the testbed. In contrast, our solution Metron is able to match the hardware limit in terms of throughput by doing two specific things. The first thing is that we are able to offload the routing table of the first network function into the Mellanox card. By doing so, input packets match their entries in the network card and can be directly dispatched to the correct CPU core that undertakes their processing. This can be done while ensuring zero inter-core communication among the components of the service chain. And this is why our work demonstrates a whole new performance level for NFV service chains. This can be also obtained by using only a small fraction of the available capacity at the server, and Metron demonstrates 6.5 times better efficiency compared to the state-of-the-art. Now I'm going to explain to you some reasons why existing NFV systems lose performance. To do so, I will use a service chain of two functions deployed on a server with 4 CPU cores and 1 network card. Now I will try to dissect the 3 most prevalent packet processing models in the NFV so far. The first model is a software-based approach which uses a dedicated switch to interact with the overlay network functions running on different CPU cores. E2, ClickOS, and NetVM are example systems that use this packet processing model. If we inject a packet through the service chain of this system, it takes 4 inter-core transfers. The next approach is a hardware-assisted version, which uses the receive-side scale functionality of modern network interface cards to hash and dispatch packets to 1 or more reception threads. These threads are then pipelined with processing and transmission operations, and example frameworks are NFV and Flourish. Injecting a packet through this service chain now takes 2 inter-core transfers. The last category is also a hardware-assisted version, which uses either RSS or flow director to dispatch packets to a core where the reception thread is now collocated with the first network function. Then packets are transferred to a second core where we collocate the second network function with the transmission thread. OpenBox, SNF, and FastClick are example frameworks using this approach. Injecting a packet through this service chain now takes 1 inter-core transfer. So I'm going to inject another set of packets in parallel into all of these systems so that you can observe the relative latency to traverse these service chains. Presumably, the fastest system is the one with the fewest inter-core transfers. At this point, I would like to highlight a fact. The available time for a server to process a 64-byte packet at the speed of the 100 gigabit network is only 5 nanoseconds. However, all of these systems are transferring at least once every packet, either via the DRAM or the last level cache, and this operation itself takes several nanoseconds. So there is a very clear mismatch between the requirements of a 100 gigabit network and what existing NFV systems do in terms of processing. Now I will explain to you how our solution Metron can achieve zero inter-core communication. But before I do that, let me summarize the problems that we have seen so far in the literature. The first problem is that all of the existing works greatly underutilize hardware. For example, modern network interfaces can do a lot more than simple hashing of packets, as they provide both traffic classification and dispatching capabilities. Moreover, available programmable switches and GPUs can also provide similar functionality. Therefore, the challenge that we face is how to better exploit all of the programmable hardware available today while dealing with hardware heterogeneity. To do so, we use an industrial-grade controller that provides unified management abstractions for heterogeneous hardware. and we extend this controller to be able to manage commodity servers for NFV purposes. The second problem, as we have seen already, is that all of these systems introduce too much inter-core communication. This is a particularly hard problem because real systems need to dynamically adapt to changing workloads, and when new cores are allocated to serve this purpose, it is very hard to guarantee that these cores will never exchange any packets. We solve this problem by early applying traffic classification and tagging in hardware, and then by using these tags, we can map them to the correct CPU core that undertakes further processing at the server side while ensuring zero inter-core communication. This results in our system being able to provide 4.7 times lower latency, up to 7.8 times higher throughput, and up to 6.5 times better efficiency compared to the state of the art. Now I will give you a brief overview of Metron by using a concrete example. Let's assume that we have a simple network that consists of a programmable open-flow switch and a server with 2 CPU cores. Let's also assume that we want to deploy a simple service chain of a firewall followed by a DPI. First, we input this service chain to the controller, and then we use our earlier work called SNF to synthesize the input network functions into a single, highly optimized equivalent packet processing graph. SNF guarantees that in this graph, read and write operations occur with zero redundancy. In the next step, Metron takes these read and write operations and splits them into 2 parts. A stateless part that can be offloaded into hardware, while the stateful part will remain in software running on the commodity servers. At the next step, the controller associates each stateless operation with a tag that will be also mapped to its stateful operations at the server. Now Metron is able to deploy the service chain by installing the hardware operations to the available components, meaning the OpenFlow switch and the network card, and by deploying the software operations at the server side. At the runtime, the switch that is used in this topology is tagging traffic such that it will be then dispatched by the network card to core number 1. Also, network elements and servers report their runtime load statistics to the controller so that it can be used for load balancing purposes. So when a load imbalance occurs and core 1 gets overloaded, the controller will immediately detect this imbalance and split the traffic class that is affected into 2 parts. Each part will be associated with a different tag, and when this tagging will be enforced into the data plane, then input traffic will be tagged in a different way such that it can be load balanced across the available CPU cores. Now let's proceed with the performance evaluation of our work. We begin with a 40 gigabit deployment using 2 commodity servers and an OpenFlow switch. One server is used as a traffic generator and receiver, while the other server deploys a firewall to DPI service chain. We begin again with the hardware limitations of this testbed in terms of throughput, which, as we measured, is around 38 gigabits per second. First, we try the emulated E2 system with this specific service chain, and our linear fitting to the yellow triangles of this graph shows that this system, each additional core in this system is able to sustain 1.7 gigabits of throughput. By deploying the same service chain with OpenBox, our linear fitting suggests a higher throughput per core, which is around 2.1 gigabits per second. But this does not scale with all the available CPU cores. Therefore, both OpenBox and the emulated E2 cap their throughput around 25 gigabits per second. This suggests that the combination of firewall and DPI all in software is simply too costly for this service chain. And Metron solves this problem by offloading the firewall of the service chain into the OpenFlow switch, while still keeping the DPI in software. This allows each additional core, in the case of Metron, to sustain 4 gigabits of traffic, and after using more than 10 CPU cores, Metron can drive this service chain to the maximum performance. Metron also demonstrates 3 times better efficiency compared to the state of the art. And by comparing the red squares of this graph with the black crosses, we can see what is the exact cost of running DPI in software. To summarize these results, Metron is able to provide firewall and DPI at the speed of a 40 gigabits testbed, which we consider as an important achievement of our work. Next, we show the latency perspective of this experiment, which is on a logarithmic scale. First, we observe that Metron achieves 35 to 97% lower latency compared to the state-of-the-art systems. And if we also compare the latency for firewall to DPI with the minimum latency of the hardware, these two values are comparable. Now we proceed to a 100 gigabit deployment, which is the exact same deployment I showed earlier in this talk. The focus now here is to dissect the performance contributions of Metron. We begin with the total performance of the Metron system with this example service chain, which, as you recall, is around 76 gigabits per second. And now I will start removing each of our key contributions one by one to show you what performance penalties are expected or actually occur when you don't actually apply these contributions. First, we disable hardware offloading, and we get the results shown with the blue triangles in this graph. The difference between these two graphs quantifies what is the performance penalty for not being able to exploit the underlying hardware. Then we deliberately choose the wrong CPU core to dispatch traffic, and we get the results shown with the pink diamonds. The difference between these pink diamonds and the red squares, which is Metron, showcases what is the cost in terms of performance for introducing unnecessary inter-core communication in the service chain. Now, by disabling both hardware offloading and accurate CPU dispatching, we get the results shown with the gray pentagons. I hope this use case helps you to clarify why our key contributions are essential for realizing high-performance service chains. The final part of the evaluation is a 10 gigabit deployment of a service chain that consists of a firewall followed by a stateful NAT gateway. In this use case, the traffic generator injects variable bitrate load into the system because we would like to stress the load balancing capabilities of Metron. The first graph shows you what is the input load offered by the traffic generator in gigabits per second. And as you can see, there are multiple peaks and values in this graph because we would like to stress the abilities of Metron to adapt. The next graph, shown with black dots, shows you the throughput of the Metron server while processing the input load. We can see that our system is able to dynamically and precisely adapt to the changing conditions. And in our paper, you can find more information about our dynamic CPU core allocation. Here we also present some of our open source activities, which include a driver for managing commodity servers as part of ONOS SDN controller, and our high-performance data plane, which extends fast click. To conclude, I have presented Metron, an NFV service chaining platform that operates at the true speed of the underlying hardware. With Metron, we make the following contributions. We orchestrate available heterogeneous programmable hardware to perform both traffic hardware offloading and accurate CPU core dispatching while ensuring zero inter-core communication among the service chain components. We also provide quick and stable adaptation to changing workloads, and in our paper you can find information and results about our low-cost service chain placement policy. Thank you very much. I'm happy to take any questions.
So we have time for a couple of questions. Questions?
Hi. So I have two questions. The first one is, how do you define efficiency here?
So efficiency in our graphs is the ability to accommodate the same throughput, for example, using much fewer CPU cores.
So higher efficiency means lower CPU core usage.
Yes, meaning same result in terms of throughput, but using fewer resources. In this case, it's CPU cores, yes.
Okay, so the second question is, so how do you virtualize different programmability on different heterogeneous programmable NICs? So suppose like the server have 2 programmable NICs. One is have national NICs, another one have the liquid IO NICs from Kelvin. So if you have such kind of platform, how do you virtualize the computation results on these 2 hardware?
Right. So there are several kinds of abstractions that we use to achieve this result. First, we use DPDK-based NICs, and in DPDKs, any kind of NIC is actually exposing the same features on the northbound API. So it doesn't matter which vendor you use. If it's a DPDK-based NIC, will expose the same information on the controller side. And regarding our control plane, we're also able to deal with other types of heterogeneous hardware in a unified manner. In our testbed, we showed how to obtain unified information from both network interfaces and OpenFlow switches.
Dejan from AT&T, very interesting one. I also have 2 questions.
Yeah.
So first question, for service function chains spanning multiple servers, can they still benefit from your solution?
Right, so we consider in our work that the most efficient way in terms of performance to deploy a service chain is if you collocate everything in one machine. And not only this, but also collocate everything in one single core. This is why we use our earlier work SNF to synthesize all the functions of a chain into a single component. So we really believe that this is the way to go if you really want to achieve high performance. You don't have to deploy the different functions of a service chain across multiple machines, because this implies performance penalties.
I see. So the second question is, for your evaluation, you did experiment for service chain with 2 or 3 network functions. How about longer chains, for example, with 4 or 5 even?
We don't have such a service chain in the paper, but our solution is generic, and with our earlier work, we have shown that we can apply the same synthesis approach even for chains of 10 functions. So I don't see that this could be a problem in our work.
Yeah, thank you.
All right, last question? Yeah, just one though.
Okay, one quick, Yotam Akon from UC Berkeley. Could you comment very shortly on how you decide which part to offload to the hardware and which part to not offload, and how that combined together, I mean, logic-wise, to a valid result?
Right. So when we deploy Metron on a specific hardware, we know which operations can be offloaded. And in this particular case, we state that hardware offloadable operations are the stateless ones, because we use commodity hardware such as OpenFlow switches, which are not able to deal with state. So whatever is stateless in this case can be offloaded, and whatever can be supported by OpenFlow or network interface cards. Now the stateful part is still at the server side, and to connect these 2 parts, we just use a unique tag. This tag will be applied by the hardware, and then at the server side, we know that this tag has to be sent to a specific port.
All right, let's thank Georgios one more time. And we now continue with the second talk of the session, which will be given by Kay Zhang. So Kay is a pre-tenure